Okay.
Right. It's my pleasure to introduce Voon, who is a new postdoc in the group. She started working with me just in February, so she's only been here about 2 months or so, and of course only a month really in person. So Voon comes, her transition through her career so far, she started and did her undergrad at Berkeley in geophysics, and she did some of her undergraduate research with Doug Draeger. Then she went on to Caltech, and she just finished and defended her PhD in November in 2019. And she has a very wide, interesting background in many different parts of seismology. This varies from aerial seismology and infrasound using balloon type techniques to looking at the very deep part of the earth, looking at the core mantle boundary. So structural work, both from the core mantle boundary, but also in basins and crustal structure. And then today she's going to talk about some of her work that has a impact on source side understanding of seismic events, and also not just earthquakes, but looking at debris flows. So without further ado, let's please welcome Voon, and thank you very much for coming, for agreeing to do this at the very last minute. Thanks.
You're welcome, and thank you for the kind introduction, and thanks to everyone who is joining online. I hope you're all doing well, and I get to meet you all in person in near future. And I'm also thankful for this opportunity to speak to you all on how we can describe seismic signals generated by debris flows. And this project was one of my PhD projects at Caltech and was supervised by Professor Victor Tsai, and is in collaboration with Professor Mike Lam, Alex Baer, and Tom Ulizio, who are part of the geomorphology group at Caltech. So as a seismologist, I'm interested in using seismic waves to learn about dynamics processes such as earthquakes and explosions. The seismograms that we record is a combination of many elements. So first, it reflects the effects of the source, which is how seismic waves are generated, and the earth structure, which is the medium that the waves travel across, and finally gets recorded by the instrument itself, which we hope we know best. And so for source studies, we often use moment tensor, which is a mathematical representation of force couples that describes the amplitude of the seismic waves radiating out from a point source. And information of structures can be obtained by developing velocity models through methods such as seismic tomography. And here is an example of velocity model of a sedimentary basin where we have shear wave velocity with depth at a 1D and also a 2D profile. With good information of the structure and a mathematical way to describe the source, we can generate synthetic seismograms and use them to study many different types of source processes, including here, which is an example of my current work of trying to model volcanic eruptions at Hawaii. And this has worked really well for sources that produce long period signals. But we are also interested in understanding processes that produce seismic signals at higher frequency, above 1 Hertz. So for many of these signals, the major contributor is often anthropogenic, meaning human-induced. So for instance, we can see this great example of railways in Southern California, which is the blue line. There are also several seismic stations marked in red on the map. And the plot on the right shows seismic traces at different distances along the track for over a few hours. The train motions generate strong seismic signal from 1 to 10 Hertz, which is marked by the gray traces. Sorry, I can't see my cursor. Okay, the gray traces here. And then outlined in this black envelope, and we can trace how the train moves along the track from the move outline. And the V shape that you see on the plot with 2 different slopes is quite interesting because it means that there are 2 trains that are moving in opposite direction. And on a more relatable note, We can also see that the reduction of seismic signal at 1 to 20 hertz range as a result of the COVID-19 lockdown. And this is an example from Belgium, where we can see the peaks of the noise during work days and the trough during the weekends and when the lockdown was initiated, which is marked by the red line. And then once it passed the red line, we see a very dramatic decrease in the overall seismic signal. We also see a very similar effect in Canberra, shown by the seismometer located near the Parliament Hill. The high frequency signal is not limited just to anthropogenic factors. The seismologists have also noticed that the sediment flux in rivers can contribute to this high frequency signal. And it is more apparent in this example from Taiwan, where the amplitude of the velocity increases during a major storm, shown in black, and compared to the base level, which is the gray line, because there are more sediment being transported down the river. And this is exciting because if we can describe these seismic signals like what we did for earthquakes, we will be able to use them to investigate the dynamics of these non-earthquake environmental processes. So, and one of these processes that we are interested in is debris flow. So in this talk today, I will first like to introduce how the seismic signal looks like for a debris flow observed at Montecito in California. Then I will describe a mechanistic model that captures the underlying physics of how debris flow generates these signals. And with the model, I will discuss how it can be useful to design a robust early warning system for this particular hazard. So let's begin with a little bit of background of debris flow. So the debris flow risk in Southern California tends to increase after wildfire. So what happened was that vegetation from the steep sides, the steep hillsides keeps the soil intact, but when the wildfire happens, the vegetation is burned, so causing the sediments to become unstable and rolls off the slope and accumulates in the different river channels. And during an intense storm, this water can move these sediments and initiates a debris flow. And we see that this is the case for Montecito, which is located in Southern California and along the Pacific coastline in between Santa Barbara and Los Angeles. So in late December of 2017, there was the Thomas Fire, which is the second largest wildfire in California history that burned through the hills above Montecito, as seen from the Landsat satellite photo. And after the fire, an unusually large winter storm occurred on the early morning of January 9, 2018, and initiated a large debris flow which sent mud, water, rocks, and boulders from the hill towards the coastline. And to understand the scale of destruction, the pictures here shows a single-story house which is entirely covered with mud and large boulders. And you can see for the boulders, these are at least 4 meters wide. And there were several casualties, 21 people, and hundreds of houses are damaged and or destroyed. And here's a map outlining sort of the watershed boundary of each creek and where the debris flow deposits are. They are mostly confined along 3 main creeks here. And the whole episode is recorded by a seismic station from the regional network located near the coastline. And there's also a weather station which recorded the rainfall data. The weather station recorded intense rainfall around 3:40 a.m. And the intensity is about 13 millimeters per 5 minutes. And to give a context, yesterday's rainfall in Canberra over 24 hours is around 15 millimeters. And soon after the rainfall, we first noticed that there is an increase in amplitude shown by the seismogram in broadband in black and filtered at 5 to 10 hertz, which is in red. And plotting this in a different manner where we look at the power spectral density at 5 to 10 Hertz, which measures the seismic power given the frequency, we can see that the amplitude peaks around 4:07 a.m. and quickly subsides. We can also plot out the seismic power for each frequency at different time. So the y-axis represents the power and the x-axis represents the frequency in Hertz. Each curve represents a timestamp from the beginning, which is like the light color, towards the peak time, and from the peak time towards the end of the sequence. And the black dashed line is the baseline prior to the base energy level prior to the debris flow event. And plotting the data in such a manner shows many patterns. So first, we see that overall the seismic power rises and falls with time. Secondly, we see that the peak frequency, where the power is maximum, increases with time. And so it's like the peak here, even though the amplitude has dropped, but the peak frequency, the maximum is increasing in the x direction. And we also see that there is an increase of the amplitude at 3 Hertz and below, so it's around this range. And we believe that this is due to the standing wave phenomenon in the creeks from the rainfall. So here's a cumulative plot of power at all frequencies over time. And this debris flow signal is very strong, especially at around 5 to 15 Hertz. This signal is particularly unique and is distinguishable from other types of natural sources. So for instance, we look at a seismic station along the coast where Hurricane Isaac landed. Again, this is power versus frequency and period. We see that the power increases for most of the frequencies higher than 0.1 Hertz compared to the background level, which is estimated by these two gray lines. But the power increase is not comparable to what is observed by the debris flow, which is above the red line. And earthquakes could also produce very strong high frequency energy, but this energy at 5 to 10 Hertz often does not sustain over 10 minutes due to attenuation. And in addition, there are also characteristic P and S wave onset in earthquakes, which are not observed in debris flow. So in short, we see that debris flow signals are pretty distinct, and just like how we can represent earthquake sources with moment tensor, now we want to introduce a model that can describe the debris flow signal. With that, we take inspiration from the river transport model that was proposed by Victor Tsai et al. In 2012 and later improved by Gimbert et al. In 2014. The general idea is that each sediment particle impacts the riverbed and creates a force impulse, which then excites seismic wave that travels and gets recorded by a nearby seismic station. And with many particles, each impacting the riverbed at random times relative to the others, one can evaluate the sum of the energy by looking at the power spectral density observed at a given station. So we can imagine some of the parameters that are important, including a representative size of the particle bed load. On the right, we see an example of power spectral density recorded by a station at some R0 distance away from the riverbank. So in this case, it's 600 meters. The size of the particle matters, so the larger particle generates stronger power spectral density than the medium and the small particles. And if the station is closer at 200 meters, we can see that the power is higher overall, but especially at the higher frequency. And this can be attributed to the path effect, as higher frequency seismic energy is preferentially attenuated with distance. And this curve will modify slightly if we consider more elements such as noise generated by water flow, which is investigated in Gimbert et al. 2014. So debris flow is slightly different from a river model in terms of how the particles impart forces on the bedrock and the rate of impact. So in debris flow, the boulders in the snout are being pushed by the flow behind and dragged along a rough surface. So you can imagine this is like a washboard, and maybe perhaps not, since we don't use this anymore, where a fabric is dragged along the groove, dragged over the grooves. So when multiple particles impact the rough surface randomly, its velocity departs from the average flow speed, but like a fluctuation. So it's no longer like a steady state shear, and the fluctuation is the one that gives out a high frequency signal. And here we only consider the contribution of the snout, which is shown in the diagram. And this snout is rich with the biggest boulders in the debris flow. But the debris flow does have multiple regimes which can contribute to the high frequency signal. And since we published this work in 2018, Maxime Ferrin et al. Have updated this and further investigated the impacts of all the elements. So with that, I will refer the audience to their paper in 2019. So the expression of the seismic power in a function of frequency f takes into account of many parameters, hence the length of the equation. But I want to highlight that the essential components that affect the power are the particle impact term, and which describes the forcing, and the wave propagation term, which describes how the Rayleigh surface wave propagates from the source to the recording station. And we can slightly simplify the equation with the assumption that the ground and particle densities are similar. So we can cancel out the densities here and get a slightly shorter equation. In debris flow, we're interested in knowing the location of the source and also important flow parameters, and the equation provides these answers. So in the next few slides, I will go through each parameter in this equation and show how that the distance to the source depends on the peak frequency, and the debris flow properties like the dimension of the snout, the particle size, and flow velocity controls the amplitude. So first we will solve for the peak frequency, which is something that we can measure from the observation. So we have seen this plot before of power versus frequency over time. And we can measure the peak frequency by finding the maximum of the curve. And from the equation, we can also take the derivative as well, and that will give us an equation of R0 as a function of peak frequency, and with other constants such as Vc, which is the Rayleigh wave phase velocity at 1 Hertz, Q, which is the term that controls attenuation or how seismic wave decays in energy each cycle, and Kasi, which is a scaling parameter on how velocity increases with depth. And here, this plot shows the peak frequency measured every 30 seconds over a duration of half an hour. The color represents the amplitude, so the darker the color, the stronger the peak is. And since we have an equation, we can convert the peak frequency into distance. And what we see here is that the peak frequency increases with time. That means the flow gets closer to the station, which is located downstream. We can estimate the distance at the time of the strongest amplitude, so which is 1.2 kilometers, and correlates with the zone of major damage along the 2 river creeks. So given as well that we know the time and the distance, we can measure the average flow speed, which is about 2.4 meters per second. And coming back to the equation which describes the power curve, we have now we have all the components now to find this product that relates to the debris flow properties, so LW, D cube, U cube, which are the length of the snout, the flow width, the representative boulder diameter, and the flow speed. And these terms are interrelated and all contribute to the signal simultaneously. But what we can see that the terms that really dominate the power is the boulder diameter, or the particle size, and the flow speed, because they are scaled to the power of 3. So from the creek channel we've observed in the field, we can get estimates of the length and width. And using the flow speed measured earlier, we can estimate the boulder size, where D at peak amplitude is about 1.3 meter. And at later times, when it reaches downstream, it reduces in size, which is compatible with the loss of momentum, where the bigger boulders are deposited earlier in the sequence. And these estimates are comparable with what is observed in the field shown in the picture here. So we show how this debris flow signal can be explained physically, which takes into account of important parameters, including boulder sizes and flow speed. And now we can ask if we can measure this debris flow. Can we use it to give a warning for debris flows that are damaging with large boulders flowing at high speed? The current way of early warnings for debris flow incorporates our understanding of how it happens. So one of them is a forecast-based method from USGS. It's based on burn severity, the topography of the region, and the soil characteristics. So this map on the right shows the Thomas fire parameter. So Montecito is around here, and the previous map only shows a small part of the region, but we can see that the fire actually burned through a large region, and many mountainous areas are considered high hazard, including the slopes above Montecito. Another method is like a smoke alarm detector, where a stream gauge measures the water level and sends warning if the water level reaches certain height or changes rapidly. And this method is also used in lahar detection. A similar method is also used for lahar detection at volcanic areas. Walter et al. In 2017 developed another method, which is Seismic Base. They apply the amplitude source location ASL method, which is used to detect tremors, to an array of stations located near the drainage channel system in Switzerland. And this method considers relative amplitude measurements, where stations close to the source has the highest amplitude, and the amplitude decays geometrically with distance. So that's shown by the curve right here. And using this difference in amplitude, they can grid search and track the flow front as shown in the map. And this is a very powerful technique, but at the same time, it still relies on relative amplitude and a group of stations. So alternatively, our model, which describes the absolute amplitude, allows us to set a power threshold for damaging debris flow. So the frequency used to measure the power determines the distance that the warning is sensitive to. So for instance, in this example from Montecito, the threshold is marked by the gray line that gives us a couple of minutes before the most damaging front hits. Likewise, weaker flows or damaging flows that are far away from the region will fall below the threshold and not trigger the system. And this threshold is unique to debris flow and will not be exceeded by other natural signals. So shown here for the same station, we measure the power for the entire duration when the station is operating, and see that only the debris flow exceeds the threshold substantially. And of course, in Montecito, the station placement is not ideal because it's located at the end of the drainage channel. But we can envision that a better strategic station placement can give us more warning time. And this can be made even more robust with multiple redundant systems, including putting more stations and incorporating techniques that was previously mentioned. There are certainly some challenges with a threshold-based method where there can be other events, not necessarily natural events, that exceeds the threshold. So on top of the top plot shows the signal again from the debris flow, both the seismogram in velocity and the spectra in frequency. And at the bottom is an example of electronic glitches at the station, which can happen due to a power outage, network connectivity issue, or just sensor malfunction. And so, but for lucky for us, that these glitches have a particular character where the signal is a white noise with almost constant power at all frequency up to the Nyquist frequency of the instrument. And this is a raw PSD measurement of the station with glitches, and we can see that it does exceed the threshold multiple times. But knowing the character of the glitches and also the expected frequency range of debris flow, which is about 5 to 15 hertz, we can de-glitch by rejecting data with amplified power from 20 hertz to Nyquist frequency in real time, and solve the issue and be able to keep track of the threshold in real time. However, there are anthropogenic sources that can interfere with the threshold. So for instance, the data below here is obtained from another regional station where we noticed there have been some renovation work going on at the site. So that was based on how the signal only happens during working hour. And it shares very similar signature with the debris flow with the same similar strength, same power, so, based on the color, and spans the similar frequency range. And hence, if it's used for the threshold-based method, this cultural noise will exceed the threshold. And in this case, we'll need to complement the threshold method with other types of methods, or incorporate information if we know in advance that there will be strong cultural noise near the sensor. But however, what I think was the biggest uncertainty in the model was that the elastic parameters of the subsurface through where the waves are traveling is not very well have a lot of errors and can not be as accurate as it could be. And these are the parameters that we usually lump sum and call it as the path effect. So at Montecito, there is no in situ measurement. So we rely on the measurements in the neighboring area to get the phase velocity and attenuation. And these measurements are also important for earthquake hazards. So there have been a substantial effort to compile them for the Los Angeles region, but it might not be readily available in other areas. The phase velocity is estimated from a sonic borehole data from a nearby basin, and attenuation is estimated from regional earthquakes using the T-star method. But even with the estimates, we can see that the attenuation factor Q covers a wide range of value from 20 at a fault zone to 100 at a kilometer depth. And this uncertainty can carry forward into errors in our measurements of distance R0 and the debris flow parameters LWD cube UQ. So returning to the concept where seismograms are a combined effort of source and structure, I hope in future to focus on ways to improve our measurements of the structure, like getting better handle of these elastic parameters, especially shallow attenuation, so we can reduce uncertainty in the source side. So with that, as a summary, we observed that the debris flow excites strong high-frequency seismic signal, which can be described with a mechanistic model. This power is controlled dominantly by the boulder size and flow speed. And being able to describe the absolute amplitude, we can create a threshold-based warning system, but to make it more robust, we should improve our knowledge of the shallow structure. So with that, and thank you, and I will take any questions.
Thank you. So those who do want to ask questions, you can raise your hands in the on the participants box, or type something in to the chat, and we'll see how we go. Of course, I do have one question immediately, and maybe it may not be something that you're looking at answering, but I'm just wondering, one of the big questions in the whole riverbed erosion and so on is getting a handle on how much the rocks and various pebbles and tools and things can erode the bed, and I wonder if that is is Victor's original model that you were talking about. Victor Tsai's original model, is that about? Did that originate in that direction from trying to learn how rivers erode their beds, or is it spinning out the other way?
It's actually started off with they're trying to understand how much sediments were being transported in rivers. So they recognized that it was a important problem to understand tectonic history, and also just how geomorphologically things are changing. But then it's very difficult to put instruments to get this kind of measurements. So that was the original direction. And then they realized is that if they can properly account for the forcing term, they can use it for almost any flow problems. So including debris flow, avalanche. So yeah. Any other questions?
I have a comment or suggestion, maybe.
Yeah.
I wonder about the anthropogenic sources and whether you might be able to distinguish them by looking at a sort of broader band measure of the energy, just because you wouldn't expect them. I wouldn't have thought they would be as energetic as a debris flow. And just looking at your spectra, it seemed like they were very sharp. And if you integrated over a broader frequency range, you might be able to distinguish them.
That might work. So the renovation happens to be a jackhammer. They were like rebuilding the road in the area. So it was like a particular very high frequency noise. But I think the main problem was that the debris flow, if you want it, we can't go too low frequency because there's not enough signal. So if we look at between 5 to 10 hertz, the certain cultural noise just also happen to also occupy that space. So if you use a threshold, you see the same power. But I think this is when it's like prior information, like, okay, knowing that there was a wildfire and then a winter storm is coming, so the chances of having a debris flow is significantly higher. Those things can be incorporated into it. Or like knowing that rain has arrived and then sort of incorporating those data.
Okay, thanks.
Yeah.
Penny, did you have a question, or is that a suggestion to people how to raise hands?
I couldn't find the raise hand thing. It's gone on my computer.
It's disappeared.
So that was a raised hand. I really liked that talk, Voon. It was really interesting, and like those debris flows is just such a huge hazard for that area of California. I had a question that kind of relates to this slide that you're showing, the cultural noise, but also the Swiss example that you gave. And I'm wondering if you can, and this might be something that's not a hazard assessment tool, but is a tool for figuring out how the debris flow moves. I'm wondering if you can use the multiple seismic sources to look at how the debris flow moves.
Definitely.
By triangulating, and then that will also help you get rid of your noise.
Definitely that will work. Yeah.
Yeah. Okay. You might have said that and I didn't get it.
I guess I did sort of specify that for Montecito, there happens to only have one station that really recorded the debris flow.
Yep. So but could you do it here with this Swiss one?
Yes, but I didn't have the data, so we didn't look into it. But yeah.
Yeah. Because it could be really important for, as you mentioned, the lahars, because there's tends to be a longer run-up distance than the debris flows in these really steep areas.
Yeah.
So it'd be really useful for, such a cool area. Thanks for teaching us about this.
Always. I think Shub has a question.
Hi, Ben. I had a question about the deglitch mechanism that you applied to remove the electronic noisy things. If you could go to that slide.
Give me a second. I have it on a different screen.
Yeah, this one.
Okay.
So when you remove those glitches, you also remove some of the data points. Do you see? I was just wondering why, if the mechanism that you have applied to remove this, it removes some of your data as well.
So I guess maybe I should have these thresholds are ideally, if we are doing it as a early warning manner, they will be calculating the power spectra over in real time with overlapping windows. So what I did here was rejecting certain data means you also have to how should I explain it? So while rejecting the data, because of the overlapping window that I use, I also use a median filter. So that also rejects the neighboring points, but it's only in like the 30-second time period. But if the debris flow signal is like what was shown on the graph, the median filter would not distort that kind of signal. So it would get rid of a lot of the artifacts, including the data gap as well, but not the debris flow. I don't know if that answers your question, but it's part of the processing that removes some of the artifacts.
Okay, cool. Thanks.
Yes, Malcolm.
Voon, lovely talk. In the application to hazard, I missed what sort of density of seismic network you might need, what sort of distance scales, given the frequencies involved here. Do you have a feel for the distance scales between the stations and the flow that you'd need?
I didn't have we didn't thoroughly investigated that route, but then my hunch is that like if the station is, we can strategically put the station closer where the debris flow source would be instead of being at downstream, so that would buy a lot more time, and every station like 2 to 3 kilometer range would be sufficient, I think.
Okay.
Yeah.
Well, I think that's been a fantastic seminar. Thank you very much, Voon, and thank you to everyone else for attending. It's great to have a big audience of people. No matter no matter how often we do this, I'm always surprised at having so many members of the school and others joining in. They are recorded. There is a YouTube channel with all of these past talks on them, or all of the ones where people were happy to have them recorded. So that's something that I encourage everyone to go back and look at if you haven't seen all of the seminars. So thank you once again, Voon, and we'll draw the seminar to a close. Thank you very much to everyone. Bye-bye.
Thank you.